Hello. In this video, we will see the properties of exponential growth, the logistic equation, and using some real-life data from the COVID-19 pandemic. We will discuss the basic models that are used to explain the dynamics of outbreaks. First of all, we have to look at the geometric growth or geometric series, sometimes it's called. The rule for creating this type of series is take the first element of the first number in the series and multiply it with a constant, and this will give you the second number in the series, and you multiply the second number with the same constant. In this example it's 2 and it's shown in red. By multiplying the second number with this constant, you'll end up with the third number in the series, and you multiply the third number again with this constant, you end up with the fourth number in the series. This is called geometric series or geometric growth time to time. This rule can also be described as such. You multiply the first number in the series with a constant and add the result of this multiplication to the first number in the series, to the same number, and you end up with the second number. In the second row, you see such a description, which is exactly the same with the previous one. It's only a different description. So you multiply the second number with this constant. Here, this in the second row, this constant is 1, and shown in red. And you add the multiplication, result of the multiplication, to the second number, and you get the third number. And you multiply the third number with this constant again, and add it to the third number. So it can be seen as... there's also another example with a different constant. This time it's 2, and it's also given on the third row, and the constant is shown in red. The constant is 2. So multiply the first number with this constant 2 and add it to the first number. You end up with the second number, and you multiply the second number with this constant again and add it to the on top of the second number, and so on and so forth. These are two different descriptions for the same series. Well, and you can see here the general form of those descriptions. The second one, in the second term in the box is, or equation in the box is, you multiply the y with a constant. The constant is k plus 1 here, and you end up with the second or the next number in the series. The first equation in the box describes the rule as an addition of a certain value which is proportional to the value of the y, and the proportionality constant is k in that case, and you multiply the value of y with k and add it on top of y to find the next number in the sequence. Actually, as you can see, these two expressions are can be derived from one another. Actually, it's all very simple, basic manipulation. Okay, in the graph you can also see what y and y plus 1 means. Y plus 1 doesn't mean that you add 1 to the y. It means the next y value in the series. And y plus 2 means 2 numbers after y. And y minus 1 means 1 number previous to the number y. So on and so forth. There is one important point here. We will explain this in detail later, but you have to accept it as is at the moment. This is also, this geometric series or geometric group is also is very similar to exponential functions. Exponential functions are shown, the general form is shown in the box number 1. And there is a constant a in the first equation, and that the relation between the a and the k is given on the third box. So we will see why this is, but at the moment it's an important point here is that geometric growth and exponential functions are closely related. For a quick review, y plus 1 means the next value for next x in the series, x plus 1. You can see it. Actually, here the description in the second box does not give you a relation between an x and a y. It is more a series type of description. The first one gives you an expression which tells the relation between the x and the y. However, you can also think about the second expression or second description as a relation between an x and the y. We will come to that. K times y is the value you add onto y to find the next y value in the series. And in the second box, you multiply it with multiply the y with a constant multiplier and find the next y value in the series. And that constant multiplier is k plus 1. And the first two descriptions are exactly related to the exponential relation. And we will see why. But the first term, the first one is y equals to the e to the a times x is a continuous function. And the second one, the y plus 1 is equals to y times k plus 1, is a discrete definition. You can write it down like this. Y is equal to e to the a times x. So the next y is x plus delta. Delta is a factor which is constant. Every time you add to the x, you find the next x. And when you plug it into the equation, you'll find the next y. Next y means y plus 1. And you can open up the bracket in the third line, and you can actually separate this exponential function into two. As you can see, the first term in the red circle is exactly y. And the second term is a constant. It's constant because e is a constant, a is a constant, and delta is a constant for this expression. I mean, delta, you can choose delta whatever you want, but for every step it is a constant. So it's actually similar to k plus 1. So as you can see, if you see or try to describe this continuous function, this exponential continuous function, as a series, then you end up with the geometric growth. So they're exactly the same thing, in a sense. If you make the steps smaller and smaller in the geometric series, you end up with the exponential function. And the relation between the a and the k can be seen here. So k plus 1 is equal to e to the a times delta. K plus 1 is related to not only a, but also to delta, because as you can understand, if the delta is big, you mean your steps are larger, and the growth or the increase between these steps should also be larger. That's why k is k plus 1. The multiplying constant is dependent on delta. Okay. There is a small reminder here that we'll see this in detail in the next video, but keep it in mind. Probably you know it, but the derivative of an exponential function is an exponential function. And if the a is 1, the derivative of an exponential function is exactly the same with the original function. It's an interesting property of the exponential functions which make them unique. The important thing we have to understand, which is important for us to understand the dynamics of pandemics and epidemics or outbreaks, is that the derivative of an exponential function is grows or increases in proportion to x, and it's exactly proportional to the value of y. This is an important point we have to keep in mind. Why the epidemic models or the outbreak models predict exponential growth? So the model is simple. We assume that we have an homogeneous population, and there is a single individual which is who is infected, and it walks around and displays random chance encounters with other members of the group of the population, and there is an average number for this. So not every individual every day meet with the same number of individuals, but you can have an average value for this, and it's pretty much constant for a large population, homogeneous and large population. So at the end there is E people, let's say, that this single person meets every day on average. This is true for the whole population. However, not all these encounters ended up with a transmission, disease transmission. So there is a probability of P that each of these encounters results with a transmission, disease transmission. As you can see, if there is no encounter, there is no disease transmission. First thing that should happen is an encounter, but not every encounter ends up with transmission of the disease. So actually the number of people at the end of this day got infected is E times the P. So there's E number of encounters, and there's a probability of P that these encounters will end up with an infection, which means that if the probability is 0.5, so half of these encounters will end up with an infection. So every new infected person, now there are 3 people here, will do the same the next day. That's why the number of new cases every day increases with the number of infected people. So as you can see, what we can write down is that the next day the number of infected people, n plus 1, is equal to the number of infections that day, which is basically n times k. K is the number of new cases a certain individual creates every day through its interactions. So if there are n individuals, then n times k new infections will occur. And if you added this n times k number on top of the individuals that are already infected, you find the total number of infected people the next day. So this equation 2, tells you exactly this. And the equation in the row 1 below is, as you know, a different way to write this. So to remind us, n plus 1 is the total number of the cases the next day. N is the total number of cases that day. N times k is the new cases added on top of the already existing cases. And k plus 1 is called the daily multiplier. Actually, if the k is a constant, which means that the behavior of the people in the society does not change and their interactions do not change, so the probability of transmission and average encounter does not change much. So k is a constant, and which means that every day you have to multiply the number of infected people with k plus 1. You'll find the number of infected people the next day. So as you can see, this behavior is exactly a geometric series, which means that what we see is an exponential growth. That's why, this mechanistic model, that simple one, but a very robust one, explains why the growth of infected people with time, at least for the beginning of epidemics, is an exponential. Let's talk a little bit about how the data is represented. First of all, even though the growth of infected people is a continuous function or a continuous process, usually the data is gathered not continuously but in a discrete manner. Either new infections are recorded every day or every week, so represented in a discrete fashion. So it looks like a geometric series. You either give the total number of cases, or you can also give the new cases every day. You have to, first of all, notice that there are 3 scales in this graph. There is a scale for the derivative of the exponential function. There is a scale for the exponential function, and there is also another scale for daily multiplier. The daily multiplier is the one shown in yellow. The blue ones are the cumulative number of cases, which is the exponential function, and the bar graphs are the new cases, daily new cases, which is in a sense the derivative of the exponential function. You can see that the derivative of the cumulative cases, the exponential function, is exactly the same with the exponential function. This is what we talked about. If you scale them correctly, the derivative of an exponential function is exactly the same with the exponential function itself. So the daily multiplier you can see here is the k plus 1, which is, if everything goes stably, is a constant. And n times k is the number of new cases created each day, which is kind of the derivative of the function. And the cumulative number of cases is shown in blue, is the n changing by day, which is an exponential. Now we have to give the description of doubling time. It's a concept which is quite important. When we look at the formula here, the description of the number of n, for example, after a certain amount of days, like say 5 days or 4 days later, what will be the number of total infections, or the cumulative number of infected cases? How many folds there will be an increase? So to understand that, it's actually what you have to do is, when you think about it, to find what's the number the next day, you multiply the number of cases that day with k plus 1. To find it 2 days later, you multiply this n times k plus 1 with k plus 1 again. And find the number of cumulative cases 3 days later, you have to multiply this again with k plus 1, which gives you n times k plus 1 times k plus 1 times k plus 1. So as you can see, it is, say, k plus 1 to the power of days, which will elapse. For example, if you have a k plus 1 value 1.2, around 1.2, which means that after 4 days, the number of cases, the number of total infections will be double, almost 2 times higher. And the important thing is, it doesn't matter which day you start. Whatever day you start, 4 days later, if k plus 1 is a constant, 4 days later, the number of cases will double. So 4 days is called the doubling time of this growth. But this does not, this exponential growth does not continue forever. There are 2 reasons. There are actually many reasons, but 2 main reasons for this. The one is, first of all, as the number of infections gets higher, so even if the average encounter number does not change, many of those encounters cannot end up with an infection, because people are already infected. I mean, this person encounters with already infected people. So, as you can see, the probability of these encounters ending up with a new infection goes down. So E times P, K, will go down, which as the number of infected people increases, K goes down, decreases, and when everyone is infected, actually K goes to 0, because there's no way a new infection can be created. Okay. Of course, this is a very hypothetical situation. This can only happen if infected people continue their daily routine all through the course of the outbreak, which is not the case. And also, after a while, they recover and become immune, and they're not contagious anymore. However, if the spread of the virus is very fast, so you can end up with people continue with their routine until they get sick. Most of the population can already be infected. This is the case with in small closed populations like summer camps or dormitories and things like that, with very fast spreading diseases like measles. But in other cases, this is a very simplistic model. So as the K gets smaller with the number of infected cases, or the cumulative number of infected cases increases, so the daily new cases decreases, and the daily multiplier decreases. There is also other reasons why the K decreases. There will be interventions. So when the disease starts, some precautions are taken. Usually, this is the natural response of the population. There are two types of precautions. One is aiming at decreasing the transmission probability, and the other one is quarantine. Two ways you can decrease the transmission probability. For example, you prevent the mass gatherings of people, like concerts and things like that. So the meeting chance decreases, which decreases the E. Or you can enforce mask usage or hand washing and things like that, which decreases the probability of transmitting the disease, even the encounters occur. Usually, these two precautions are taken together, which decreases the E and the P, which decreases the K. This happens even before the significant number of people got infected in the population. The quarantine, on the other hand, is restricting the population size, which means that you restrict the population. Infected individuals can encounter and transmit the disease too. So you can, for example, quarantine certain regions of the city, certain cities, certain countries. So the infected people cannot encounter with the population in general. This limits not the E or the P, but this limits the total number of cases that can be infected. These are two main precautions you can take, which decreases the K value, K plus 1 value. As we mentioned before, we assumed for exponential growth that the individuals who got sick or who got infected continue with their daily routine and continue to get other people infected all through the outbreak, which is not the case. And this is, and the K is constant. K plus 1 is constant, which is not the case either. So K decreases with time. Even if you don't intervene, K will decrease with time. To describe this situation, you can use a logistic function. Logistic function decreases the K value of the K, in proportion to the number of total infected cases. As the total infected cases increases, the K decreases. This is not a precise description of the outbreak dynamics. However, it's simple enough to understand it, and it can describe the situation good enough. But we will describe a more precise model, mathematical model for the outbreak dynamics in the second or third video. For the time being, we will use the logistic function and deem it good enough for our purposes. So what happens if the K value of K decreases as the number of cumulative cases increases? As you can see here, the first part of it, exponential. The K or daily constant K plus 1, shown in yellow here, is pretty much constant until the day 9, 8, 9, which shows an exponential growth. Then the K plus 1, the daily multiplier, starts to decline significantly. And this decrease changes the behavior of the cumulative cases from exponential to a linear function. Then the rate of increase starts to decrease, as you can see from the bar graphs, and then the daily new cases, the number of daily new cases goes down to 0, K plus 1 goes to 1, and the cumulative cases do not increase anymore. It comes to a saturating point. Well, we say that the cases are peaked, which mean that not the number of cumulative cases reaches a maximum. the number of daily cases reached a maximum, and then they start to decline. Peak describes that point, which is also the inflection point of the cumulative cases. Let's give some examples from the real-world data, examples from European countries and Asian countries. These are the cases reported during the first days of the first months of the pandemic in 2020. So these are winter and spring months. As you can see, in South Korea, it's almost a textbook example of a dynamic. You can see that in the first 10-12 days of the outbreak, it's an exponential growth. Of course, you have to notice that the data is noisy, because even if we're talking about averages and being constant and things like that, there is some random noise on the data. This is not everything is not stable as we assume to be in our theoretical discussion. Nevertheless, you can see that the yellow points, which represented the daily multiplier, is hovering around some certain value around 1.2, 1.3. Then, due to some strict interventions, it drops very dramatically, and you can see that it also decreases the daily number of cases, new cases. Then the cumulative cases, the blue ones, becomes linear and then goes to saturation. So this looks very much similar to the logistic equation we talked about one slide before. However, in United Kingdom, which did not take serious precautions until the end of the first month almost, you see that the exponential phase continues for a long time. The yellow squares, which represented the daily multiplier, hovered around 1.2 line, in an average of 1.25, which means that during that period, the doubling time is around 3 days. So every 3 days, the number of cases, cumulative cases, doubled. You can see that the exponential phase continues. However, the k plus 1 value, the daily multiplier, is decreasing. It's not constant, which means that even though the exponential phase going on, the linear phase or the peak is coming, but we do not see peak here. The daily new cases continues to increase during this period of time. In Germany, you can see that the daily multiplier, which is shown in yellow, is around 1.25 or quite close to 1.25 for a long time. Then it starts to go down clearly after 27th or 28th day due to some strict lockdown precautions. And you can see that the daily number of daily cases stop increasing. This indicates, and the cumulative cases increasing not exponentially but in a linear fashion, and which means that the peak is coming. Which the peak is not seen here, but the peak is approaching. When we look at Spain, Spain clearly shows a peak, but the peak is, as you can see, not very sharp, but spread out. And the number of cases started to decrease. The number of new cases, daily new cases, started to decrease. So it goes to saturation. But until 23rd or so, actually the daily multiplier, which is shown in yellow, is quite high. And then it started to decline dramatically due to some strict regulations applied at the red arrow shown there. The case in Italy is similar to Spain. You can see that the first 20 days or so, 19 days, the daily product is quite high. And then it starts to settle down around 1.2. But then, due to strict regulations shown with the red arrow, it started to decline, and also the daily new cases increase dropped, and it then started to decline. But the peak has occurred. But the peak is a kind of spread out peak compared to the South Korean. We talked about mainly the early phase of the outbreak, the dynamic of the case growth in the early phase of the outbreak. In the next video, we'll talk about a little bit about exponential functions, and on the third video, we will derive some more realistic equations about the dynamics of describing the dynamics of the outbreaks, and we'll talk about them in more detail. See you in the next video.